Okay, so we'll continue our overview of compilers, and today we will focus on register allocation and instruction scheduling. So first let's draw that picture that we drew last time. So the compiler, we have the front end, we have the optimizer, and we have the backend. Okay, and let's try to remember what each one of these does, just to review what we covered in the previous lectures. So what does the front end do? The whole front end, yeah. What's the function of the front end?
Scanning.
Yes, go ahead.
Yeah, the scanning, parsing, and semantic analysis.
Okay, so scanning and semantic analysis. There is one other phase, parsing. So it's scanning, parsing, and semantic analysis. So what do these all combined do? What's the input and what's the output of the front end? The input is source code. And what's the output of the front end? Yes?
Abstract syntax tree.
Yeah, an intermediate representation of the code, which is typically an abstract syntax tree. And the abstract syntax tree is a tree representation of the code. And we have seen an example last time. Now, in this middle part of the compiler, we have the optimizer. So last time, we gave an example of the optimizations that take place here. What was that example?
Sub-expression elimination.
Yeah, exactly. So it's common sub-expression elimination. And last time we mentioned that the optimizations that take place here are intended to be machine independent. So they are not low-level optimizations that target a specific machine or that try to do good utilization of the capabilities of the hardware. Optimizations that try to maximize and optimize the utilization of the hardware are here in the backend. So the backend is intended to have those low-level optimizations that make the best use of the available hardware, that optimize the code on a specific hardware. So in principle, this should be machine dependent. The backend is machine dependent by nature, while the middle optimizer is supposed to be machine independent. But last time we said that in practice, these optimizations here are not going to be strictly machine independent. Their nature has nothing to do with the machine. It has to do with the code, right? In common sub-expression elimination, it's an optimization that has to do with the code itself. It's trying to eliminate some redundancy in the code, or it's trying to do some kind of reuse. So the idea here in common sub-expression elimination is reuse. Instead of computing something multiple times, compute it once and then reuse it. That's the idea. Now, this reuse requires resources. So when you reuse something, you want to store it somewhere. So you have to store it somewhere in some place so that you can reuse it. But that place that you store it on, it has to be fast enough. It has to have easy access. If it doesn't have easy access, then that defeats the purpose. So if you don't have a fast enough device that you store this thing in, you will not you will not do an optimization. It may be just faster to recompute instead of reusing. And having said that, this means that for this kind of reuse, the best storage device for this is the register. So you want it to be in a CPU register, which is the fastest storage device. And when you keep doing optimizations like this that require reuse and storage and require registers in particular, you are increasing the demand for registers. And increasing the demand for registers is not a good thing. Increasing the demand for registers may end up slowing performance. Why? Because you have a limited number of physical registers on the machine. So this is something that we will face in the back end. There is a limited number of physical registers on the machine, and if you have 200 different variables in your function, 200 variables, and you have 300 temporaries, why do you think that the generated code will have temporaries? So there are the original variables that are in the source program, and there are temporaries that the compiler will generate. Why do you think those would?
You got to swap in and out of registers?
Not necessarily. So let's look at our example. In fact, the example that we will be doing today, A times B plus C divided by D is assigned to X. And exactly, intermediate values. So if we look at the abstract syntax tree, we'll have A and B, they will get multiplied. But the result of this multiplication has to be stored somewhere, right? And then C and D, they are divided. And then you take the result and you add it. And then you assign to X. You assign this to X. Now this intermediate result, when we wrote some the assembly code for this, we wrote the code like this. Load A into register R1, load B into register R2, then multiply R1 and R2 and put the result in R3. Now in this code, we have 3 registers. Register R1 holds an actual program variable. Register number 2 has a program variable. Register number 3 has a temporary. It has a, it doesn't correspond to a program variable. It stores some intermediate result, which is the result of the multiplication between R1 and R2. So it corresponds to this node in the abstract syntax tree. So in general, the code that is generated by the compiler, it's generated, the first step in the code generation is this abstract syntax tree. And some compilers may immediately convert this into some linear representation like this. Some compilers may delay this a little bit and work on the tree representation of the code. So, this is what we call a tree representation or a graphical representation of the code. And this is a linear form, a linear representation of the code. And last time, we said that usually a compiler uses multiple representations, multiple intermediate representations throughout the compilation process. So it will typically starts with the tree representation, then it moves to a linear representation like this, which is abstract assembly. Then it will start making this abstract assembly more real, targeting the real machine. So here we have a program with some 200 variables and 400 temporaries. And the machine has 16 registers. So you cannot put all the variables and all the temporaries in CPU registers. So there is a competition for registers. In fact, this is going to be the main topic in today's lecture. But the point here is that, optimizations may require more registers. They increase the demand for registers. They increase what we call the register pressure. And when that register pressure increases, not all registers can be, not all of these virtual registers can be stored in physical registers. So some of these virtual registers may end up in memory. We will see this in detail in today's lecture. But when they end up in memory, that's slow. So this means that, we could end up slowing the execution. So some optimizations that appear to be good and they are eliminating redundancies or they are doing a lot of reuse, they may end up increasing register pressure, increasing the competition for registers, and some of the variables and the temporaries will not be stored in registers. They will be placed in memory, and in that case, our execution may slow down. Okay, so in the back end, we have instruction selection and instruction scheduling and register allocation. So we talked about instruction selection last time. So what's instruction selection? Yeah.
Most optimized method.
Okay, the best sequence of instructions for the given code. So you can either apply instruction selection, you can apply it to a tree representation of the code. You can apply it directly to a tree representation of the code, or you can apply it to a linear representation of the code like this. And then you want to decide, what are the best or what are the best machine instructions for implementing this. So this could be one-to-one mapping. So we could just map these abstract assembly instructions to actual, concrete instructions on the target machine. This is possible, but sometimes this may not be the most efficient way. Sometimes, what was the example that we presented last time? Yes?
The load taking multiple cycles, so rather than having a multiplier wait on the load, have another load between those two to make up the...
Okay, so that was instruction scheduling. But now we're talking about instruction selection. In instruction selection, what was the, a better sequence for these three instructions on the target machine? Yes?
You said there was certain machines that the multiply could do it from two loaded variables rather than registers in either.
Two memory locations. Yeah. So if the machine, we are doing this assuming that the machine does not have a multiply instruction that can operate on memory operands. But if the target machine has an instruction, a CISC instruction that can operate on memory operands, we can replace this sequence of three instructions with one instruction that operates directly on memory operands instead of loading the first, loading the second, and then multiplying. So instruction selection is about utilizing, making the best use of the instruction set that is available on the target processor, making the best choices and using selecting the most efficient sequence of machine instructions for this intermediate representation. Remember that this is still, this abstract assembly is still an intermediate representation. By the way, can you think of an algorithm that takes you from this tree that converts this tree into this abstract assembly? Yeah.
Just traversing the tree.
Traversing the tree. What kind of traversal will give us this?
I'm forgetting the words for this.
Okay. So what kind of traversal? will help us in this case. Will get us from this abstract syntax tree to
Depth first.
yeah, it's depth first. And can you explain why depth first?
Because you got to go down the tree to hit A, and then you got to back up and hit B and then multiply them together for the operation.
Okay, so we need the depth because if we are here, we want to perform the add. We cannot perform the add until we completely compute this left branch and this right branch. So we cannot do the add until we do everything below it, until we completely compute this and completely compute this. But we cannot compute the multiply. We cannot do the multiply until we do everything below it, everything beneath it, right? So this is a depth first by nature. In this case, we have, these are the leaves. So leaves are loads because we're loading these variables. Then when we get to the multiply, you multiply register 1 with register 2, and then you load C into register R4, sorry, and load D into register R5, and divide what? Divide R4 and R5. And put the result in R6. Then, so we have traversed this and traversed this, and now we are here. So we need to do add, yeah. So this result here is in register R3, and this is in R6, right? So dividing R4 and R5, we have this result in R3 and this result in R6, and then we need to add R3 and R6 and put the result in some other register like R7. And now the result is here in R7. So what should we do with it? Yeah, set it, store it in. So the assign is a store. We will, we will cover this in more detail when we get to code generation. But this is just, in this case, it's just so intuitive. This straightforward conversion from this abstract syntax tree to this abstract assembly. Store R7 into X. Okay. So, and here the most important observation here is that when we are constructing this abstract assembly, we are assuming that we have an infinite number of registers. So this assumption is one of the main things that make it abstract assembly. So it's not real assembly yet. It's not real because we are assuming that we have as many registers as we want. So what did we call these registers? Virtual registers. So these are not real registers. We're just using as many registers as we need. So these registers are virtual registers. What the register allocator does, the register allocation phase in the compiler, what it does is that it maps these virtual registers into physical registers, as we will see in a minute. Okay, we will see how it does this mapping of virtual registers into physical registers. Now I have to make a note about these A's and B's that I'm using in my assembly. I think I pointed out that real assembly does not have variable names, right? So real assembly, machines are not aware of variable names. A machine doesn't know variables, is not aware of the whole notion of a variable. A machine knows storage locations. So it knows registers and memory locations. That's all what the machine understands. The machine doesn't understand variables. But What are we implying here? If you remember from lecture 1 or lecture 2, when we are using this variable name here, what are we implying?
Address.
Yeah, the address of this variable in memory. And in fact, let's introduce the notation in the book. So in the textbook uses a language, an intermediate representation called ILOC, which stands for Intermediate Language for an Optimizing Compiler. ILOC, Intermediate Language for an Optimizing Compiler. And in this language, a load instruction is written load address immediate or activation record pointer address of A into R1. So what I'm writing here, this is a shorthand for this. This is a shorthand for this. What does this mean? So this is load address immediate. So this is a load instruction that takes an address and it takes an immediate operand. So the address is in a register. This register has a pointer to the activation record for the current routine that we are compiling. And this address of A, this is an immediate number that represents what? It's just a number that's the offset, exactly. The offset of variable A. So since we will be using this, let's clarify it even further. So if you have a main function, your main function, a program with a main function, the main function will have an activation record on the stack. This activation record has the local variables, and it has the parameters, and it has the return value and the return address for every function. This is what we mean by the activation record. When main calls function 1, the activation record for function 1 will get pushed on the stack. When function 1 calls function 2, the activation record for function 2 will get pushed on the stack. So each function, each active function, has this location on the stack that we call the activation record for this function. And it has the local variables of this function. It has the parameters of this function. It has the return value, and it has the return address and other things. So this is the activation record. So when function 2 completes, what will happen? When function 2 completes executing and needs to return to F1, the activation record of F2 gets popped off the stack. So now each of these activation records will have an address associated with it. So if we are in function 2, the address for function 2 could be, for example, 0xFF10. So this is the starting address of F2. So if we are compiling, if the compiler is currently compiling F2, then this is the starting address of, let's make it 0, 0. This is the starting address of function F2. And the function F2, has variables A and B and C. So the address of variable A is this starting address, which we assume is stored in a register that we call activation record pointer register. So it's a special register that holds the starting address of the activation record of the current function. So in this case, it's going to have 0xFF00. So to compute the actual address of a variable, for A, it's going to be this, 0xFF00. That's going to be for, variable A. For variable B, it's going to be 0xFF 0, 4, assuming that we have 32-bit variables. So this is going to be offset 0, this is offset 4, this is offset 8, assuming 32-bit variables. And for C, 0xFF08. Okay. So this is the notation in the book. So a load instruction takes the activation, a register, which is in for a local variable. The base is the activation record pointer, the address and the activation, the register that holds the activation record pointer, and this is the offset for the variable. And what I have here is just a shorthand for this. It's understood that we are assuming that variables are local variables and all addresses are relative to the activation, to the starting address of that stack frame. And A is not a variable, it's in fact an offset. Okay? Questions on this? All right, so usually we will just do this shorthand. We will not write the full the full syntax of the assembly in the book, or the abstract assembly. Okay. Now how does the compiler, how does the register allocator map these virtual registers into physical registers? Now let's assume that we have, or the target machine has 3 physical registers. If the target machine has 3 physical registers, so let's call them P1, P2, and P3. So we have 3 physical registers on the target machine. And how many virtual registers do we have here? 7. So the job of the register allocator is to do the mapping between these. So how will it map them in this case? Well, it's going to say, okay, register R1, I'm going to map R1 to P1, the first physical register, and I'm going to map R2 to P2. Now, here, obviously we need two physical registers. Now this multiply now is multiplying R1 and R2 and putting the result in R3. The question is, for R3, do we need a new register, or we can just reuse P1 or P2? So why can we reuse? Yes, we can reuse.
Because they're not used again.
Exactly, because they are not used again. So because R1 and R2 are not used again, we don't have to use a third physical register. We can just reuse R1 or R2. So we can say, okay, R3 is going to get mapped to P1. Because after this instruction, we do not need R1 and R2 again. To explain this further, assume that we have an additional instruction like this: add R1 and R7 and put the result in R8. Now, if we had an instruction like this, would have this allocation been legal? No, it won't be legal. Now, here for R3, you cannot reuse the register for R1 because I still need it. I still need it here. So I still need to keep R1 in a physical register until I get to this instruction. So basically, you always need to keep a virtual register in the same physical register until you are done with it, until the last use of that register. So with this instruction in red added, I won't be able to reuse P1, but I can still reuse P2, right? P2, R2 is not used. So with the instruction in red, I can reuse P1. I cannot reuse P1, but I can reuse P2. So in register allocation, and by the way, we are not describing an algorithm now. We are describing the concept. We are trying to use the minimum number of physical registers, or at least use the registers that we have, and we are trying to make, to do as much reuse as possible. Okay? So if we had an instruction like this, then we would say that the live range of register R1 is going to be this much. So this is what we call the live range of register R1. So register R1 got defined here, and it got used here and here. So the live range of a register is the distance between the definition. This is where we are defining it. We are putting a value in it. Okay, we're storing a value or a result in it. So it's defined here, and it's used here and here. So this is the live range of register R1. So register R1 has a long live range with this instruction in red. While where's the live range of register R2?
It's just those two below.
Yeah, just the first three instructions. So this is the live range of R2.
It's the one below it.
Would the live range start at the second instruction?
We are using it here, right? Oh, yes, you are right. Sorry. Yeah, so this is where we are starting with the definition. Yes. So this is the live range of R2. So this is the definition, and this is the last use. While for R1, this is the definition, and this is the last use. Okay. Questions on the concept of a live range? Okay. So the point here is when we have longer live ranges, we have a stronger competition for registers. So we say that we have high register pressure. In fact, by register pressure, we mean the number of registers that are live at a certain point. We will say more about this later. But let's now get back to this example. So let's now get rid of this red instruction. Now, if we get rid of this instruction, then the live range of R1 now becomes this. Live range of R1. Okay. So now we can do again, we can use P1. Now for R4, what can I use? Let's say that we will always use the physical register with the smallest number that is available. So what will be available to us to use for R4? P2, exactly. So for R4, we'll use P2. Of course, if we use P3, it will be perfectly fine. But we're trying to use the minimum number of registers here. So R4, we can use P2. For R5, we must use P3, right? Because here at this point, we have registers R3 and R4. Both of them are live. So here, when we get to this point, R3 is live because it got defined here and it's used here. So this is the live range of R3, right? And the live range of R4 is this. So at this point, R3 and R4 are still live. So we cannot use the registers of P1 and P2 for R3 and R4. We must use a third register. Clear? Okay. So for R5, we must use P3. Okay? And for R6, now, so which registers are no longer live at this point? R4 and R5, right? R4 and R5, after we execute the divide, we no longer need them. By the way, we are assuming that, you know, this instruction, you can reuse the registers that you are using for the input for the source operands of an instruction, because you will read these values before you write to the register that will hold the result. So that's why we are able to reuse the registers that are used for the source operands of an instruction. So now R4 and R5, they're not used below this point, so we can just reuse either P2 or P3. We will reuse P2. And now for R6, so R3 is in P1, R6 is in P2, right? And in fact, after we are done with this, you know, at this point, after we are done with R3 and R6, we can use any register that we want, right? So for R7, you can use anything that you want. And let's stick to the rule of using the smallest number. So we'll just use P1 for R7. And then we store P1 into X. OK? So in this case, we managed to map virtual registers into physical registers. And we could do it with 3 physical registers. Now let's assume that we only have 2 physical registers.
Store something in memory.
So now assume 2 physical registers, P1 and P2. So that's all what you have. Now let's redo it with 2 physical registers, see what happens. OK. So now we can do, you know, R1 in P1 and R2 in P2. There is no other way of doing it. You know, but we have two of them. So we put this in P1 and this in P2. Now we have this multiply, and we need a register for the result. Without that red instruction that I deleted, we can reuse either the register for R1 or R2, because we assume that it consumes the source operands before it writes to the destination operand. So we can put R3 in P1. Now we need a register for R4, so we can put it where? Where can we put R4?
P2.
In P2. Now we need a register for R5. This is where we hit a problem. Now we need a register for R5, and we have, you know, R3 and R4 at this point. We are looking for a register for R5. Now R3 and R4, the ones that have the registers, are they live or dead? They're live because we are using R4 here and we are using R3 here. So live means that they will get used later. So both R4 and R3 are live. So we can't reuse P1 or P2. But we need a register for this. So what we can do here is that, OK, we can say that this R3, we can store it in memory. So the register allocator in this case would generate a store instruction, store R3, which is, you know, P1, store P1 in a temp. So this temp stands for a temporary memory location. Or let's call it, to be explicit, let's call it M or mem temp. OK? Now we can use this register P1 for R5. So now we can say R5 goes to P1. So now this is P2, this is P1. When we divide P1 by P2 or P2 by P1, and we'll put the result in R6. Okay. Now for R6, which register can we use? Now after this point, are R4 and R5, are they going to be live or dead?
They're dead.
Dead. So we can reuse either P1 or P2. Okay, because R4 and R5 will no longer be needed. So we can say, okay, we'll put R6 in P1. Because both of these guys will not be needed after this instruction. Now we need R3. But virtual register R3 is no longer in a physical register. So it's not in a physical register. We stored it in memory. So what do we need to do? What's the logical thing to do? Load it, yeah. Bring it back from memory. So we load that memory, that temporary memory location. We store it into which register? What are the options that we have? We only have one option.
P2.
P2, because P1 has R6 in it, and we still need R6. So the only option that we have is P2. Okay, so now we can, add. So basically adding, P2 and P1, and then we can put the result. Once we are done with this, we can use any register we want. So we can put R7 in P1. Okay. Now what's the point here? The point here is that with fewer registers, when we have 2 physical registers instead of 3, the register allocator could not map each virtual register to a physical register. It had to do some storing and loading. So in this case, R3 did not get mapped entirely to a physical register. In fact, we put it in a physical register temporarily. Then we stored it in memory. Then we loaded it again when we needed it. So this kind of store, we call it spilling. With the terminology of compilers and register allocation, this is a spill. So we basically spilled it to memory because we don't have enough room for it on the register file. There is no room for it on the register file, so we spilled it to memory, and here we loaded it again. So this means that when we have high demand for registers, the register allocator will not be able to accommodate all the virtual registers. It will not be able to find a physical register for every virtual register. So it will be forced to do spilling. It will be forced to spill some of them to memory. And obviously, these stores and loads that we are adding, that we call spill code, obviously these are slowing the execution. These are going to slow the execution. We are adding instructions. These instructions are going to be using machine resources. They will use functional units, and they will use all the machine resources, and they will be using the memory system. And the memory system has a limited bandwidth. So you are executing more loads and stores, and that's slowing your execution. So the job of the register allocator is to do the mapping with minimal spilling. The job of the register allocator is to minimize these spills. Try to accommodate all the virtual registers and map them to physical registers. Any questions on on these concepts.
I have
Yes.
a question now. With the architecture of today's processors, when it spills over into write to memory, wouldn't it go into the L1 cache?
Oh, even if it does, well, generally speaking, we can never control if something is in L1 cache or not. But most likely, when you are spilling, these spills are going to go to the stack.
Yeah.
And they're going to the stack, and they are getting reused within a short period of time. So they are very likely to be in the L1 cache. So it's most likely you will be hitting the L1 cache, or things will hit in the L1 cache, and there will not be cache misses. But even if you hit in the L1 cache, this is still slower than storing them in a register. L1 cache is still slower than the register. Accessing L1 cache will take 2 or 3 cycles, while accessing a register is instantaneous. You can access the register immediately. So definitely L1 cache is much faster than main memory. So L1 cache, you can access it in 2 to 3 to 4 cycles, while main memory, to access main memory, you need hundreds of cycles. So it's 2 orders of magnitude. On modern processors, it's 2 orders of magnitude faster than main memory, but it is still slower than a register. And you are also using other resources. You are using the memory system. And your memory system has a limited bandwidth. You are executing more memory operations, and memory operations are expensive. So your memory system has a limited bandwidth. Overall, you have limited resources on the machine. And these instructions that you are adding are just going to use some resources. They will use issue slots. So it's an instruction that will use issue slots, and it will use an issue slot that could be used for another instruction. Okay? Yeah. So we would expect spill code to hit in the cache most of the time, but even if it hits, it will still slow the execution. Of course, if it misses in the cache, it's a huge performance hit. Any questions on the concepts of register allocation and spilling? Okay, so is it crystal clear? Yeah. Okay, so unfortunately, optimizations tend to increase the demand for registers, and one of these optimizations that increase the demand for registers is the common sub-expression elimination that we described last time. The other one is the other optimization in the back end, which is instruction scheduling. So instruction scheduling increases the demand for registers. So we only described instruction scheduling briefly, but we will describe it in greater detail next time, what instruction scheduling is. So the idea in instruction scheduling is hiding the latencies of the loads. This is a multiply that uses the result of the load. So why don't we just execute another instruction while waiting for the load to complete? So this is a brief and possibly vague description of instruction scheduling, but next time we will explain instruction scheduling in detail. Okay? All right, so I will see you. Any questions before we end the lecture? Okay, so